Okay, this is AQA AS 2019 paper 2, practical skills and multiple choice. Question 1, we have this diffraction pattern and we have our distances from the central maximum, which we can assume is C, I guess. So there we go. They're saying that because the resolution is 1 millimeter, the distance between that we're measuring, the distance between the dots, the uncertainty is going to be 2 millimeters because you're going to have the 1 millimeter uncertainty at either end of the ruler. That's up for debate, but we're going to go along with it for now. Oh, there we go. 1.1 is asking, why is it greater than the smallest division? So measurements are taken. Distance is measured by measuring between 2 points on ruler, and there's a 1 millimeter uncertainty at both points. 1.2, we're told that A plus B equals C. Calculate the percentage uncertainty in the sum of A and B. So first things first, when we add up values or take away values, we can just say that the total uncertainty is just the absolute uncertainties added together. So that's just 4 millimeters, 2 millimeters at each end. Therefore, the percentage uncertainty in A plus B is going to be that 4 divided by both the values added up. And then of course we need to times up by 100 at the end. That gives us 0.74%. It would be a different story if these values were multiplied together or divided by each other. In that case, we'd have to find the percentage uncertainty in both and then add them together. But like I said, when we're adding or subtracting, we just find the total absolute uncertainty and then go from there. So why do we end up with a different percentage uncertainty for C? Well, actually, let's find out what that is. So percentage uncertainty in C is going to be just 2 divided by a value of 544 times 100. Of course, we know it's going to be smaller, don't we? It gives us 0.37%, so half. And why is that? Well, it's because C is a larger measurement with same uncertainty, absolute uncertainty that is. Therefore, percentage uncertainty is less. So we always do multiple readings, don't we? If we have like a diffraction pattern, we don't just measure one spot or one fringe to the next. We measure 10 and then find the mean. 1.4, what can we do to minimize the risk of eye damage? We can avoid regular reflections, e.g. smooth surfaces, windows, mirrors. Of course, if we shine a laser on a piece of paper, it is technically reflecting, it's just diffusing, it's spreading out, isn't it? It's these regular reflections that we have to be careful of. 1.5, we're being asked to find out theta. So it looks like it's just going to be SOHCAHTOA. We have our adjacent there. And we also have the distance from C to E. That is 544 millimeters, so therefore 0.544 meters. We're going to use tan because we have the opposite and adjacent. Tan theta is opposite over adjacent. Of course, that is equal to 0.544 divided by 1.280. Therefore, we just need to do inverse tan of that. And we have been given our values to... we're going to go to 3 sig figs. Yeah, we're going to go to 3 sig figs because this is 3 sig figs here, so we can't go to a greater accuracy than that. So, it doesn't make a big difference anyway. So 23.0 degrees. 1.6, E is the second order maximum. We have 3 times 10 to the 5 lines per meter. We need to change that into meters per line. But it's nice that they've given us lines per meter, not lines per millimeter, so that does make it easier. So therefore, our D in our equation, diffraction grating equation, is going to be the reciprocal of that. That gives us 3.33. Better go to 3 sig figs times 10 to the minus 6 meters. Okay, we're looking for the wavelength. We're going to get n lambda equals d sine theta out. That's our diffraction grating equation. Take n over the other side. So therefore, lambda is going to be equal to our d times sine of our second order maximum. We've just found that out. Sine of 23. Divide that by, well, we know it's the second order, so n is 2. And to 3 sig figs, we have 6.51 times 10 to the minus 7 meters. Same diffraction grating, same laser, so D is the same and lambda is the same. What can you do to reduce the percentage uncertainty in the measurement of the wavelength? So let's have a look at our equation again. So lambda is equal to d sine theta over n. So if D is staying the same, then we need to make sure that we have a bigger value for theta and n, don't we? So we can use a higher order, e.g. n equals 3. Are we going to get 4? Don't know. Well, there's no percentage uncertainty in n, is there? So actually we don't care about that. So just theta will be larger. It's looking very messy now. Let's do that again. Theta is larger therefore smaller percentage uncertainty. 2.1, we have an IV graph with lots of data on. Just make sure you have same number of points on both sides of the line. 2.2, however, identify the data point. Okay, so basically, when does it stop obeying Ohm's law? So actually, it's just worth remembering that, well, for our line of best fit, it's not a straight line, is it? When they say draw a line of best fit, I wish they'd say curve of best fit, but whatever. It is going to curve over slightly like that. So you're not just going to use a ruler to draw your line of best fit, because it is going to curve over. I do believe that it stops being proportional at about the 360 mark. So I do believe it's that one. That's milliamps. 2.3, when it's behaving itself, it has a resistance of 22.2 ohms. Determine the percentage increase in the resistance of R to its value when the current is 550 milliamps. Okay, so when current is 550 milliamps times 10 to the 3 amps, I think that the voltage is bang on 14, and we know V equals IR, therefore R is V over I. That is 14 over, well, it has to be in amps of 0.55. That gives us to 3 sig figs, 25.5 ohms. We're looking for a percentage increase, so therefore we're just looking for the change in resistance. So it's just going to be 25.5 take away 22.2, so that's just going to be 3.3 ohms. Therefore, percentage change in R is going to be, any percentage is just the bit divided by the original. Then of course we times that by 100. We end up with 14.9% or 15% if we want to get to 2 sig figs. 2.4, oh my word, we have 4 circuits, right? Which one of these was used to obtain the current voltage graph in figure 3? Which one of these was used to obtain the graph? Okay, so we need to explain why the other circuits are not suitable. So let's have a look at circuit A. It's all about making sure that we can go all the way from 0 volts all the way to 14.6 volts. Basically, we need all of those voltages to be possible across the resistor. Oh gosh, these are complicated, aren't they? Okay, so we have here, what's going on with circuit A here? This is crazy. They're drawn so weirdly as well, aren't they? Okay, so circuit A not possible because first things first, ammeter not in correct position, not in series with R. You will get the full gamut of voltages, but you won't get the right current. It needs to be that current flowing through there. Circuit B, yes, the ammeter's in the right place. It's in series with R, so that's fine. But the problem is that P is in series with R. So basically P is always going to have some of that 14.6 volts, isn't it? When P is at maximum in circuit B, it's going to have half of that 14.6 volts. In other words, we can't have R getting any lower. So R cannot have less than 7.3 volts when P at maximum resistance. We know it has to be in parallel in order for this to happen. So let's just go with circuit C. No, of course, the voltmeter in wrong position. It's not across R. So hopefully circuit D is our boy. It has to be by process of elimination, doesn't it? Voltmeter and ammeter in correct places, and R can get 0 volts to 14.6 volts if we change the value of P. Not a super easy question, that one. Involves a little bit of thought and some complicated diagrams. 3.1, how does the change in quark character affect the number of neutrons? Okay, so beta plus decay. So there's our unstable isotope, mass number of A, proton number, atomic number of Z. When it decays, well, what happens with beta plus decay? Well, let's write out our actual numbers first of all. Positron is just 0 mass, basically. Atomic number is 1 because it's the opposite to an electron. So therefore, we're going to have the same number, same mass, but that means that the number of protons has gone down. So Z minus 1. So therefore, positron decay, we have a proton turning into a neutron. What's the quark composition of a proton? It's the nud and the pud. So up, up, down goes to up, down, down. Therefore, we have an up quark turning into a down quark. So one fewer protons, proton, one fewer proton, and one more neutron as it's getting turned into it. 3.2, positron interacts with an electron, resulting in annihilation. gamma photons produced. Energy of each gamma photon is that. Calculate the momentum of one of the gamma photons produced in the annihilation. Okay, so yeah, this is a weird one because it's not really an equation we come across. So we know that the energy, or rest energy of something, is mc squared. We can actually take mc as being the momentum, so therefore we can say that energy is equal to pc, so momentum times speed of light. Therefore we can say momentum is equal to the energy divided by the speed of light. I have to be honest, that's not something that's cropped up before in a paper, and it's not an equation that's on your formula sheet either, if I'm not mistaken. So that's a little bit mean putting that one in there. So I'm not impressed with that. Anyway, let's go with 0.52 mega electron volts. However, it does need to be in joules, so we're going to times by 1.6 times 10 to the minus 13 because they're mega electron volts, and divide that by the speed of light. That gives us a momentum to 2 sig figs of 2.8 times 10 to the minus 22 newton seconds. 3.3, we have a PET scanner. It works on annihilation. So we're being asked which other detector is going to be triggered. Well, if this is X in the middle here and we have P, then of course that means that one photon is going that way, but because of conservation of momentum, there must be one going in the diametrically opposed direction. So therefore it's going to be the one directly opposite. So explain it like we said, total momentum must be conserved. Therefore photons must have equal and opposite momenta or momentums. I never really got, because that assumes that the electron and positron come from exactly opposite directions, but I guess it is possible for them to annihilate at an angle, and in that case the photons must have slightly similar momenta. But we never think about it in those terms. We always assume that the two annihilating particles have equal and opposite momentums. Therefore, total momentum before the collision is 0. Therefore, the total momentum afterwards must also be 0. We have a solar sail and we have a graph of velocity against time. So what can we find out from this? Well, of course, we know that from one of these graphs, gradient is equal to acceleration and area under the graph is distance. Worth remembering that this is in millimeters per second, so let's not get caught out by that. And of course, this is in hours as well. All right, calculate the acceleration in meters per second squared of the solar sail. So let's pick a nice point. I'm going to go with the point 0.5 hours, and that is 68 millimeters per second. So we know that 1 hour is 3,600, therefore time is 1,800 seconds. And the increase in speed, well, we're looking for acceleration, so we're looking for change in speed over time, aren't we, of course? But the change in speed, notice that the graph doesn't go down to 0, so you can't just put 68 in there. It has to be 68 minus the 60 it starts at, and then divide that by 1,800. But of course, this is millimeters per second, therefore we need to times that by times 10 to the minus 3. And that gives me 4.4 times 10 to the minus 6 meters per second squared. A little bit of tolerance here, anything from 4.4 to 4.65 times 10 to the minus 6 gets you the marks. 3.6, reflectance is proportional to the percentage of incident photons that are reflected off the surface. Makes sense? Explain the effect of increasing the reflectance on the acceleration. Well, it's all to do with these photons pinging off, isn't it? If reflectance increased, number of photons reflected increases. I mean, we just saw that, no die. But therefore, that means that the number of photons whose change in momentum is 2 times their initial momentum increases. Because if a photon isn't reflected, then it just goes in and it stops, doesn't it? So it's transferring just its momentum that it has to the sail. But if it pings off, just like when it comes to forces and things like that, it's got a greater change in momentum, therefore greater impulse supplied to sail, therefore greater acceleration. It's all about that change in momentum. 4.1, we have this boat and trailer going up a ramp. We have a battery that's 24 volts, and we have the current time graph. Oh no, please don't make us count squares. I really don't want to. Well, good news is that I probably don't have to. I'm just going to look at the mark scheme. Yeah, there it is. Determine the total energy in 200 milliseconds. Ugh. So we're looking for this area underneath here, aren't we? That's going to give us the charge, because charge is equal to I times T. And so if a graph is I against T, then therefore it's going to give us the charge underneath. So I reckon the bottom bit, just the rectangle, is 3 times 8, so that's 24 big squares. I don't think we're going to go with little squares here because we're going to end up with far too many. You have to make a judgment call when it comes to you're going to count big squares or little squares. If you end up with, let's say, fewer than 10 squares, then yes, you have to count the little squares instead. So 24 down the bottom, and I reckon that's 16 squares, counting them in the curvy bit. So I think that's 40 squares. Each big square is 25 milliseconds times 10 amps. So in other words, 0.025 seconds times 10 amps. So that gives us 0.25 coulombs. Therefore, 40 squares times the 0.25, and that gives us 10 coulombs altogether underneath the curve. We need an energy though. We know the voltage is joules per coulomb, energy divided by charge. Therefore, energy is equal to QV or VQ. So that's 10 coulombs times 24 volts. And that gives us 240 joules. Anywhere from 220 to 264 apparently is acceptable. They're raised through a height of 3.3 times 10 to the minus 2. I'm just going to call it 0.033 meters. And the speed increases to 0.85 meters per second. Right, so therefore, and we have a mass as well, don't we? Determine the average efficiency of the motor. So we said we had 240 joules going in. Now we need to figure out how much of that has actually been used to raise the boat and provide it with GPE, but not only GPE, KE as well. So energy out, the useful energy out, is going to be the GPE plus the KE, so it's MGH plus half MV squared. And you know it's going to be something to do with GPE because we've been given a height. And as I always say, if you're given a height, you know it's going to be something to do with energy. So we can factorize this. So that is 180 times 9.81 times 0.033, bracket with that 2, plus half times 0.85 squared. And that gives us 123 joules. Therefore, efficiency, useful energy out divided by total energy in. Yes, we can times that by 100, but you don't have to. So that's going to be 123 divided by 240, and that gives us 0.51 or 51%. But you can put it either way for your answer. 4.3, either of the circuits can be used to reduce current surge. Thermistor, fixed resistor, blah, 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 blah. Explain with the properties of the thermistor and fixed resistor why the thermistor is preferable to using the fixed resistor. Well, of course, with fixed resistor, resistance does not change. Therefore, current will be reduced at all times, not just during the surge. But with the thermistor, during the surge, current increases, which raises the temperature of thermistor. This reduces its resistance and therefore its share of the 24 volts. Therefore, motor receives greater voltage, and so therefore it's more efficient. Not an easy question because you'd be forgiven for thinking, well, actually we don't really want a high current during the surge, so why don't we have a piece of wire, because then when the temperature increases it raises the resistance and so the current actually goes down during the surge. So yeah, not a very easy question, that one. Alright, multiple choice, my favourite. 5. What can have the fundamental units kilogram meters to the minus 1 seconds to the minus 2? Okay, so kilograms, meters to the minus 1, seconds to the minus 2. Ooh-wee, not an easy one to start with. Well, we've got a couple of common ones here. We have kinetic energy, tensile stress. Let's go with kinetic energy first because that's fairly easy. So the units of kinetic energy is going to be kilograms, meters squared, seconds to the minus 2, because it's meters per second squared. So it's not that one, so it can't be A and it can't be B. Then we have Young modulus for both of them as well. What's our equation for Young modulus? E is equal to FL over A delta L. So the units of that is newtons, meters, over meters squared, times meters again. So actually we end up with newtons per meter squared. I mean, you know, it's the same for stress, isn't it? So it doesn't really matter. So what are newtons per meter squared? Well, we know that newtons force is equal to MA. So F is equal to MA. So therefore, newtons per meter squared is the same as, well, newtons is kilograms, meters per second squared, times meters to the minus 2. So yes, one of the m's cancels and we end up with that units. So therefore the answer is D. Not an easy one to start off with. 6, which graph shows us neutron number against proton number? Well, let's just think carefully about this. Well, we have neutron number on the y-axis and proton number on the x-axis. So let's just think about this carefully. What shows the right graph for isotopes? Right, so I mean, it's an NZ plot, so I was tempted to go for A first of all because that's what it is for known nuclei, common occurring nuclei. But actually no, we're looking for a particular element. What do we know isotopes are? They have the same proton number, so this should not change, but the neutron number changes. So we should end up with a straight line going upwards. So the answer is D. Again, not an easy one, might have caught you out. 7, what's true about this decay chain? P and S are isotopes. Yeah, I reckon that's true actually, because A results in proton number going down by 2, beta ends up with it going up by 1. So if you do that twice, then that means that we're back where we started. So it has to be A. Okay, number 8. Okay, which row is right? Okay, well, first of all, they're made up of 2 quarks, so therefore they have to be mesons. Oh. Ah, no, they've tried to catch us out there. Mesons and baryons are both hadrons, and so B, C, and D can be correct with regards to that, but A cannot. Okay, let's have a look. B, positive pion. So positive pion, we know has to be up. What do we have? Plus 2/3, that's this charge. Anti-down, that's another plus 1/3. So yeah, I think it has to be B. Let's just check the other ones. Negative pion, no, that's got the wrong charge. Positive pion, once again, wrong charge. 9, what gives the number of baryons and leptons in carbon 12? Number of baryons, well, that's neutrons and protons, so there's going to be 12 baryons. Number of leptons, well, there's only electrons that are the leptons in an atom, so it has to be 6. So therefore, our answer has to be B again. Number 10, a muon is subject to the strong interaction. No, because it's a lepton. B can only decay into an electron. That might sound nice, but no, that's not true, because electron and muon lepton number have to be conserved. You have to have neutrinos as well. C is a stable particle. No, it's not, because like we said, it does decay into electrons, and it's subject to the weak interaction. Of course it is. Okay, we have the energy of photons. Is that? What's going to be true about the electrons? They're all going to have the same kinetic energy of that? No, because they're always going to have less than that because of the work function. They have a kinetic energy that's a multiple. Well, that's nonsense. C, their mean kinetic energy? No, that's wrong. Their kinetic energy has to be less than that. Of course it does. 12, evidence of wave-like properties of electrons. It's always diffraction. You can see that's going to be C straight away. That is literally the easiest multiple choice question of all time. 13, approximate average kinetic energy of a cyclist. So I don't like these ones. So kinetic energy is half mv squared. So what are we going to say? Half times 100 times, are we going to say 10 squared? That's not very fast, is it? Should we go 20 squared? Yeah, but the multiples of 10. Oh, I don't like that. Okay, so that's basically going to be 50 times 400. So that's going to give us 20,000. So yeah, closest one is going to be 10 kilojoules, isn't it? So it's going to be B. 14, we have this energy level diagram. So from E4 to E2 causes green light. What causes red light? Well, red light has a longer wavelength than green light. So that means that the frequency of red light must be less than the frequency of green light. Therefore, the energy of the red photon is going to be less than the energy of the green photon. So we're looking for a smaller, jump. So therefore, it's either going to be E4 to E3 or E3 to E2. Let's have a look. A, E2 to E1. No, that looks like it's exactly the same as E4 to E2, so not that one. E3 to E1, no, that's massive, so it's not going to be that. E3 to E2, yes, I think that's correct. Let's just check. E4 to E1, that's massive as well, so it's not going to be that. 15. Each pulse of sound waves contains 12 waves, 12 complete oscillations. Frequency is 8,000 hertz, and the speed is 1,500 meters per second. Okay, what are we being asked? What's the length of one pulse? Okay, so fair enough. We just need to find the wavelength. We know that V or C is equal to F lambda. Therefore, lambda is equal to V over F. So that is 1,500 divided by 8,000. So that gives us a wavelength of 0.1875 meters. Times that by 12, and we end up with 2.25 meters. So the answer is B. 16, we're looking for EM spectrum, order of increasing wavelength, X-rays, ultraviolet, infrared, radio waves. Yeah, that's right, so it's got to be that one. 17, frequency of first harmonic is 300. Right, we're definitely going to need our equation. The tension in the wire is now doubled. Okay, so we know that this is being doubled. Nothing else is being changed. So what's going to happen to the first harmonic? Well, like we said, nothing else is being changed. Therefore, frequency is going to go up by a factor of √2. Therefore, that's going to be 300. Therefore, that's going to be 300 times √2. And that gives us the 2 sig phase 420 Hz. So the answer is C. 18, Young's double slit, blah, blah, blah. Oh, great. So basically, we need everything to stay the same. Right, so W is equal to lambda d over S. So we need everything to stay the same. So let's have a look at A. A is wavelength is doubling, D is doubling, but then we're dividing by 4. So yes, that's all going to stay the same. So the answer has to be A. We have a wavelength of 5.8 times 10 to the minus 7, and we have 3 times 10 to the 5 lines per meter. We want meters per line for our D, so D is going to be, well, it's nice that they've again given it as lines per meter, not lines per millimeter. So that's going to be 3.3 times 10 to the minus 6 meters. We're looking for the highest order maximum produced, so therefore we're going to get our equation. Doesn't matter which way around, but I'm going to write it as d sine theta equals n lambda because I accidentally started writing it like that. We're looking for the maximum order, so therefore we're going to say that theta is 90. That means that sine theta disappears because sine theta is 1. Therefore, the maximum order produced is going to be equal to d divided by lambda. So that's going to be 3.3 times 10 to the minus 6 divided by 5.8 times 10 to the minus 7. I think I can sort out powers of 10 plus 7 on top. So that just ends up being 33 divided by 5.8. And that sounds reasonable. And we end up with 5.7. But of course, we can't end up with a sixth order above that. We can't end up with a 5.7th order, so the answer has to be 5. So that means that the answer has to be A again. 20, what changes with light as it goes from air into glass? We know that speed changes, well, as it goes in, we know that the waves bunch up, don't we? So that means wavelength goes down, speed goes down, but frequency, you should remember, stays the same. So we should just be looking at V and lambda, so it's just speed and wavelength, so the answer is C. 21, what pattern is produced from a single slit? They're not equally spaced. Narrow central maximum? No, we know it's a wider central maximum, don't we? It's like that. View bright fringes? Nope, it's got to be D. Wide central max with narrow side fringes. That is correct. Side fringes. Sounds like a haircut. What is the tension? Well, we know that each string must have 10 newtons vertically. There's our diagram, but that has to be 10 newtons there. That's 30 degrees there. We're looking for a bigger value. Therefore, the tension is going to be equal to that 10 divided by, because we want a bigger number, divided by sine 30. Why are we using sine? It's because we're not turning through the angle. We're turning away from the angle. In other words, just not turning through the 30 degrees. And that gives us 20 because, of course, sine 30 is a half. So the answer is C. 23, what contains vector quantities only? Acceleration and mass? No, mass is a scalar. B, displacement and momentum? Yes. 24, this is a moments question. What's the reaction force acting on the rod at support F? This is actually quite a complicated question. So we have a moment of 400 on the left and 300 on the right. So therefore, we must assume that there is also the weight of the beam or the rod pulling downwards that way as well. So if we have 4 times 100, 400 pulling in that direction, that is anti-clockwise. Clockwise, we have 3 times 100, so that gives us 300. Then where is the other 100? Well, that comes from the weight. We know that that has to be there, so that has to be 2 meters away from the pivot. And we know that this has to be a meter away from the pivot, so therefore the weight must be 100 newtons, because 100 times 1 gives us 100 newton meters, so we have our 400. So therefore, what's our total force pulling downwards? 600 newtons. We must have an equal and opposite force pulling upwards or pushing upwards on the rod, so therefore the answer has to be the same, so it's D. 3 objects, blah, blah, blah. Oh, okay. So they're all going to arrive at the same time, aren't they? U hits the floor before U and W. No, they're all going to arrive at the same time. So therefore, A can't be true, B can't be true. So it's either going to be C or D. So which one's going to hit with the greater speed? Of course, it's going to be W, isn't it? Because they're going to have the same vertical velocity. But of course, W has a horizontal component to its velocity as well. So therefore, it's going to have a greater speed. So the answer is C. 26. Oh, great. I think I'm going to need more space for this. This is a momentum question. So railway truck going that way, 2,000 kilograms and 1.5 meters per second. And then stationary truck of mass 3,000 kilograms. After the collision, they move together. Of course, it's going to be 5,000 kilograms then. Okay, what about the speed? Well, how much momentum do we have before? I'm going to say P total. That's just going to be 1.5 times 2000, so that's 3000 kilogram meters per second, or newton seconds. I'm going to call it that. Therefore, that has to carry over here, doesn't it? Therefore, the speed of this is going to be that momentum divided by 5,000. So, of course, the zeros cancel and we just end up with 0.6. So it's either going to be A or B. But what's happened to the kinetic energy? Well, you need to remember that when it comes to elastic collisions, total kinetic energy is conserved, but that's only when things ping off each other. If things couple together, then they literally can't have the same total kinetic energy. So therefore, the answer is B. Mass of car, blah, blah, blah. Okay, so we have a mass of 1,000 kilograms. We have a final speed of 25 meters per second. We have a time of 50 seconds. What's the average useful power output of a car over this period? Power is going to be energy divided by time. What's the energy going to be? Well, it's kinetic energy, so it's going to be half mv squared divided by time. Or in other words, mv squared over 2t. So 1000 times 25 squared divided by, well, 100. Cancel some of these. I think we can do this in our head. I'm going to be 625 times 10. So 6,250. So the answer looks like it's going to be C. 28 tensile force, blah, blah, blah. Same steel is used to make second, blah, 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 blah. Okay. Is this going to be just stress? Let's get out our whole equation for Young modulus. FL over A delta L. So we're looking for the extension. So let's swap around these two. What's staying the same? E is staying the same force as well. But then we're dealing with diameter, not area. So we can say that delta L is proportional to L over A. So therefore delta L is proportional to L over D squared. So length is going up by 2. Our diameter is halving. So that means that this goes down by a factor of 4. So therefore that means that the whole thing times by 4. So therefore it's times by 8. So the answer is D. What's the IV graph for a filament lamp? Well, we know that current is going to level out because it gets harder for the current to flow. So it looks like it's going to be B. Easy. 30, we have 3 batteries. Well, they're in parallel, so we still know that the EMF is 1.5, but they all have an internal resistance of 6 ohms. So what's the current in R? Okay, so we know EMF is equal to IR plus IR, or we're going to do the factorized version. What's the total internal resistance going to be? Well, it's going to be, there's 3 of them in series, so therefore it's going to be thirded 6 down to 2. Therefore current is equal to EMF divided by, well, it's just V equals IR, but we're talking about 2 resistances there. So that's going to be 1.5 divided by 6 plus 2, and that gives us 0.19 amps. So the answer is A. 31, we have a power of 100 kilowatts, PD of 10 kilovolts, and we have resistance of the cables being 5 ohms. What's the power loss in the cable? Now, whenever it comes to this, you can't just go straight for P equals V squared over R. No, because that V is not the V across the cables. The V is the V across the whole of the national grid. So ultimately, we need to end up with P equals I squared R. So that means we need to find out I first, and we're going to find that out from the power and the voltage. So P is equal to IV, therefore current is equal to P divided by V. So that's going to be 1 times 10 to the 5 watts divided by, actually we could have just done 100 divided by 10, couldn't we, because it's both kilo. So that's just 10 amps. Therefore P equals I squared R, so it's 10 squared times 5, so that gives us 500 watts, and they're giving us in kilowatts, so the answer is B. 32, okay, we have this circuit, so we have resistor of R there, and then we have R over 2 there, but then we have this voltmeter, but then it's going to have a resistance of its own of R as well. So therefore let's find out the resistance of this first. So 1 over R total is equal to 1 over a half, let's say, plus 1 over 1. So in other words, that's 2 plus 1. Therefore R is going to be, therefore R total is going to be a third. So therefore we have a third here, or R over 3, and we have R on top. So that means that the PD is going to be split 3 to 1 across these. Bigger resistance gets a bigger share of the voltage. So therefore, if we split 6 volts into 4 altogether, and then times by 1, we're going to end up with 1.5 volts. So therefore the answer is B. 33, the voltmeter reading halves when S is closed. So when the switch is open, V is equal to the EMF. But if it's halving when the switch is closed, that must mean that the internal resistance must also be 2 ohms. Let's say that the EMF is 6 volts. If you have 2 ohms load resistance, 2 ohms internal resistance, it's going to be 3 volts PD lost, as it were, across both. Finally, 34, what is the current in the 5 ohm resistor? Well, let's just figure out what they are equivalent first. So it's going to be 8 ohms up there because it's 6 and 2. Oh, it's going to be 8 there too. Oh, this is really easy. Okay, therefore total resistance is going to be half of that because they're identical and in parallel. So it's going to be 4 ohms. So therefore, V equals IR. So I is equal to V over R. So that's 3 divided by 4. So in other words, 0.75 amps. But that's the current in the whole circuit, but that's getting split evenly across both these. So divide by 2, and we end up with 0.375 amps. So that's our answer. So it's A. So hope you found that helpful. If you did, please leave a like. If you want to see other AQA papers, then click on the card and it'll take you to the AS Physics playlist. See you next time.